Hello, folks. So, welcome to part 37 of Learning Rust series. This is part of my 100 Days of Rust, and I'm on day 17. So, the last we were looking at was around how you can actually create enums, define enums. So, I was pretty sleepy, I guess. But basically, this is what is going on. Checking out how IP address can be defined using a struct and enum or just an enum. So here you see the kind alone is defined as the enum, but there is no other address associated with it. Here, along with the kind of IP address, you also associate the IP address. So all put together. So I mean, what an advantage over here is that you can actually use this notation and uh, and then mix this up with this and have a shorthand format. Basically, this and sorry, this part and this part, and have a shorthand format instead of like defining a struct. So it's more concise. So rather than enum inside a struct and all that. So you can put the data directly into each enum variant. So yeah, associated strings and whatnot, and then you have this function that takes the string argument, and then it's a type like it's kind of constructor basically that you get automatically just because of defining this enum. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. This is pretty cool, right? Because I mean, I think in languages like Java, you can exactly mention like the constructor and like what kind it takes, and every enum value will be providing that same set of values and whatnot. Unlike in this case where you can have different types and amounts of associated data. So different types is a very big thing, and also amounts, different amounts. Like you can have one value here and then three values here, and also different types and whatnot, right? So this is pretty cool. We've shown several ways to define data structures to store version 4 and version 6. However, as it turns out, wanting to store IP addresses and code which kind they are is so common that standard library. Yeah, this is the last thing I think we were talking about. Standard library has a definition that we can use. So here you have this. So you have IP address v4 and then IP address new. So IPv4 address new and then IPv6 address. So yeah. The interesting part over here is we actually have the definition something like this, right? So we have IP address which has enums v4 and v6, and then internally they have structs basically which has the associative function called new to create a new struct for IPv4 and IPv6, and you define the values there. So let's look at how the standard library defines. It has the exact enum and variants that you've defined, but it embeds address data inside not as strings in the form of two different structs, which are defined differently for each variant. So you can have different sets of data for each of them, and it's easier that way because like instead of like putting multiple such values here and like it doesn't have any proper meaning, right? It's just four values. Instead, you can put them together and then call them as like a single unit as like IPv4 address. So yeah, oops, interesting. So if you just double click on this, double click on this, anyways, it was interesting. I think I clicked on this one. Anyways, so this code illustrates that you can put any kind of data inside an enum variant. So you can put strings, structs, multiple values, say numeric types, just example. You can even include another enum, of course, like anything, right? Standard library types are often not much more complicated than what you might come up with. So, I mean, I don't know if this is a funny joke or whatever. Like users can come up with like pretty complicated, data structures and whatnot and types, but apparently standard library types are pretty, mostly straightforward and not much more complicated. Note that even though the standard library contains a definition of IP address, you can still create and use our own definition, basically user-defined data type and definition. without conflicting with that, standard library data, right? Because we haven't brought the standard library's definition into our scope. So I think you bring this into scope by doing this. Use standard library network, I believe, and then give this, and then you get it. Interestingly, you are not mentioning the scope over here. You just import it here, and you can use it anywhere with this IP address and all that. So we have not brought the standard library's definition into our scope. We'll talk more about bringing types into scope in chapter 7. Okay, so basically managing run projects, packages, crates, modules. Okay, we still haven't come to modules and whatnot, so I'll come back to it. So this is the example, similar example that we have now. Let's look at another example of an enum in listing 6.2. This one has a wide variety of types embedded in its variants. Yeah, so it's not just some sort of like this enum values. The thing has associated data, and it's not just like putting say parentheses and then some sets of values. Instead, it also has curly braces. That was the weird part yesterday we had in the previous exercise. So this one this one for example. So yeah, I mean here a message enum whose variants each store different amounts and types of values, different amounts of 0 values, 1 value, 3 values, 2 values, right? 1, 0, 1, 2, 3, and then different types of values also. Like integer, like signed integers that do get string, signed integers that do get 3 values. This is named fields now, right? So 4 variants, it has 4 variants, different types, has no data associated with it at all, and then has named fields like a struct does, includes a single string, includes 3 integer digit values, signed integer digit. Defining an enum with variants such as the ones in 6.2 listing 6.2 is similar to defining different kinds of struct definitions. We have seen different struct definitions. So we have the classic struct, so except the enum doesn't use the struct keyword over here, and all the variants are grouped together under the message type. So this can be of this type, this is also of this type and all that, but different structs are of different types. Following structs could hold the same data that the preceding enum variants hold. So these are called variants, so enum variants, and then associated data. So this struct we have seen unit struct or unit like struct, and then this is a classic struct. This is your tuple struct, right? So, but if we use the different structs which have their own type, we couldn't as easily define a function to take any of these kinds. Like, you can't say any of, right? Like, I mean, you could put enum message and then say quit message, comma move message, comma write message, comma change color message. That would still work. But yeah, I mean, you and then you could take that message as the parameter in your function to take any of these kinds of messages as we could with the message definers. This is a single type, right? You don't have to define many types and then have one more extra type. Instead, you just have one type. There is one more similarity between enums and structs. One moment. Well, I'm back. So there's one more similarity between enums and structs is that we're able to define methods on structs using implementation or implement. We are also able to define methods on enums. There's a method named call that we could define on our message enum. So for example, this is what I defined here, call and then self. So methods on it. And this is not an associated method, associated function, but it's a method. So method would be defined here. Write string and then dot call, and then the body of the method would use self to get the value that we called on the method on. Okay. But it would be interesting to understand how we will be able to get the value like self dot call. Okay. Dot x. Wondering how they would make it as like message. Say, oops. I mean, can you do a like coercion or something like that? I don't know. Like, how can you get the value x, for example, from there? I don't know. So would use self to get the value that you created. The body of the method would use self to get the value that we called the method on. So it's like this. So we notice that it's low. In this example, we have created a variable m that has the value message, right, string from hello, and that is what self will be in the body of the call method when m.call runs. Cool. Let's look at another enum in the standard library that is very common and useful. Awesome. Option. So I'm, I remember hearing about this long ago. Um, so yep. I think I've used a bit of this before. I'm just gonna try to use this again. I mean, like, read this again and then probably use it more now. So option enum and its advantages over null values, right? I think this is similar to Java's optional, because I remember that Java has this optional off and things like that. And then you can check if it is empty or things like that, or get the value. So this section explores a case study of option, which is another enum defined by the standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing. So it's optional. For example, if you request the first of a list containing items, you would get a value. If you request the first of an empty list, you would get nothing. So expressing this concept in terms of the type system means the compiler can check whether you have handled all the cases you should be handling. This functionality can prevent bugs that are extremely common. So basically, you need to ensure that you are handling all these cases wherein the list can be empty or it can contain items. So you should take care of both of these. So you handle all the cases you should be handling, and this functionality can prevent bugs that are extremely common in other programming languages. Okay. Programming language design is often thought of in terms of which features you include, but the features you explore are important too. Okay. Rust does not have the null feature that many other languages have. Okay, so basically it's excluding that feature. Null is a value that means there is no value. And languages with null variables can always be one of the two states, null or non-null. Okay, so I think object variables, or I don't know, some references in that. Anyways, in his 2009 presentation, Null references the $1 billion mistake. Tony Hoare, the inventor of Null, has this to say: "I call it my $1 billion mistake." Okay. At that time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all user references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage for in the last 40 years. Interesting, something to check out. Um, Problem with null values is that if you try to use a null value as a not null value, you'll get an error of some kind here, or some method on top of your whatever. Right? So because this null or not null property is pervasive, it's extremely easy to make this kind of error. Not sure how easy it is. So however, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. Okay. Problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of value being present or absent. This enum is option P, and it is defined by the standard library. Okay, so option P type generic, I believe, and it's none or some is so useful that it's even included in the prelude. You don't need to bring it into the scope explicitly. Okay, so looks like, okay, I'm not sure what this means, but I'm guessing it's like available by default. You don't have to bring it to scope into scope explicitly from the standard level. Its variants are also included in the prelude. You can use some and none directly without option. Colon prefix. Okay. The option D enum is still just a regular enum, and some D and are still variants of type option T. Okay. So it's an regular enum, and then these are variants, enum variants. Like are just regular enum, and like are variants. These are variants. So T syntax is a feature of Rust we haven't talked about yet. They are like generic. So it's a generic type parameter, and we'll cover generics in more detail in chapter. Okay, then. So now all you need to know is that T means the same. Some variant of the option enum can hold one piece of data of any type, and that each country type that gets used in place of T makes the overall option be type a different type. Yep, different T, different type. Makes sense. Here are some examples of using option values to hold some number types and string types. Okay, some 5, some E. Okay, and then none. Okay, The type of sum number is option. The type of sum number is option character. Oh yeah, which is a different type. Uh, so Rust can infer these types because we've specified a value inside the sum variant. For absent number, Rust requires us to annotate because yeah, none is like no value. So the overall option type, the compiler can't infer the type as the correspond. So sum is basically a variant of option. You can't, I mean, you can use sum standalone, yeah, it's included in the prelude without using this option reference, but it's sum is all related to option. So you put sum, it basically means option, option type, option enum, and then sum variant, right? Enum variant. So the type option type, the compiler can't infer the type that the corresponding sum variant will hold by looking only at the none, right? So none value, that is like no value. Here we tell us that we mean for absent to be of type option sign integer 30 bit. When we have some value, we know that a value is present and the value is held within the sum. When we have a none value, in some sense, it means that it means the same thing as null. We don't have a valid value, so why is having option T any better than having null, right? So in short, because option T and T, where T can be of any type, are different types, the compiler won't let us use an option T value as where definitely a valid value. Okay. Since these two are different types, the compiler won't let us use an option T value as it were definitely a valid value. Okay. For example, the code won't compile because it's trying to add an IA to an option IA. So this is 5, yes, there's value, and this is 5. Can you say 5 plus 5 10? No, because this can be none also. And this could be get an error message like this. So the trait add option sign integer 8-bit is not implemented for sign integer 8-bit. Cannot add okay. Cool. So intents. In effect, this error message means that Rust doesn't understand how to add an IIT and an option IIT because they are different types. When we have a value of type like IIT and the sign integer 8-bit in Rust, the compiler will ensure that we always have a valid value. You can proceed confidently without having to check for null before using that value. Only when you have an option, we have to check, or whatever type of value you are working with. So we have to worry about possibly not having a value, like an option, whatever. And the compiler will make sure that we handle that case before using the value. In other words, you have to convert an option T to T before you can perform T operations with it. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is null. So you don't assume that it is actually null. You instead check and ensure it is either null or not null and accordingly handle the situation. Eliminating the risk of incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly. Cool, that was my food from my mom. Pretty, yummy food. I'm gonna have to quickly finish this video and attend to it. So yeah, eliminating the risk of incorrect assuming. So yeah, in order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. So it can possibly be null, and then so you have to make it as option T instead of T. T cannot be like none and whatnot. So none is a variant of like these three none. So then when you use that value, you're required to explicitly handle the case when the value is null or like none. Everywhere that a value has a type that isn't an option T, you can safely assume that the value is in none. This was a deliberate design decision for us to limit nulls, pervasiveness, and increase the safety of Rust code. So how do you get the T value out of a sum variant? When you have a value of type option, so you can use that value. The option T has a large number of methods that are useful in a variety of situations. You can check them out in its documentation. Becoming familiar with the methods of option T will be extremely useful in your journey with Rust. Okay. In general, in order to use option T value, you want to have code that will handle each variant. You want some code that will run only when you have a sum of T value. This code is allowed to use the inner T. You want some other code to run if you have a none value that code doesn't have a T value available. So the match expression is a control flow construct that does just this when used with enums. It will run different code depending on which variant of the enum it has, and that code can use the data inside the matching value. Interesting. So can you do matching? Yep, there it is. So you have this x as mutant, some v, and then you get v equals like even changing the value. It's a reference, huh? Okay. And then this one is like empty even. Okay. As mute, as a reference. Can I get it as reference instead of mute? Mutator, additions. Let's see. Okay, there are not much examples around match, but that's fine. Anyway, I'll probably look at all these methods later because there's a lot of them. But this was interesting. As part of this video, let me try out the next exercise quickly. Let's see what it is. Enum 3 probably. Yep, enum 3. Compiling of it, oh, sorry, enum 3 failed. So we'll go to enum 3. Address all the to-dos to make the tests pass. Okay, message, implement the message variant as based on the usage below, point, state, and then state implementation, test match message call. Okay. State quit false position 0,0, color 0,0,0. Okay, and then state dot process message change color, which should be this, and then 255.0 you know, echo from hello world. So not sure what that has to do. Process hello world. Move the point 10, 15. So you add, I guess, and then message quit true. So I'm just wondering what. Oh, echo is just to simply echo the thing. Okay. So let's look at process. So process, create a match expression to process the different message variants. Okay. So basically, we'll have to create something like match, and then message, and then say the different types, right? Like change color, echo, move, and all that stuff. I'll have to first define them first of all here. So change. So let me just do this. Oops. Do this. And bring it here. So change color. Interesting. So change color, echo, and then string. Change color. This is another tuple. Huh? Weird. Okay, let me check this out. So this one's going to be a string. That's not a problem. This one's going to be a point here. Or should I say, yeah, this point should be another link. Say comma, 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 and then this one can just be like third of it, or like say it's unsigned 8-bit. Unsigned 8-bit, unsigned 8-bit, unsigned 8-bit. Yep. So that to-do is done. What is this? Say not covered. Message defined here. The match value is not is of type message. Ensure all possible things are covered. Yeah. Or by adding a match on with the wildcard pattern that's shown. Okay. No. I don't want to add wildcard. By the way, let's check out what this error code means. We have had this error code. No variant or associated. Okay. Can't. So this error indicates that the compiler cannot guarantee a matching pattern. Yes. Okay, got it. For one or more possible inputs to match an expression, Guaranteed matches are required in order to assign values to match expressions. Okay. You need some match values here. required in order to assign values to match expressions or alternatively determine the flow of execution. So terminator, hasta la vista, baby, talk to my hand, okay. Non-exhaustive patterns, SLS are not covered, okay. So encounter this error, you must alter your pattern so that every possible value of the input is matched. For types with a smaller number of variance signals, we should probably cover all these cases. Wildcard pattern can be added after all the other patterns to match anything. So this is the match stuff that we looked at for long ago. So we can use the arrow mark and whatnot. So I can say, I mean, if it's of type quit, then I can just call quit, I guess. Self.quit. And if it's of type, say, message change color, for example, message change color, and it's say should probably say x comma y comma z, something like this. Yeah, and then probably call it as like self dot change color. Okay, so I can say just color. Huh? The color is not defined here actually. Can I say color? Color colon nothing here? No. Can I just say in color is nothing over here? So I'm just gonna go ahead and say x comma y comma z or RGB because it's color, so why use XYZ, right? It's not some point. So let's say RGB and then RGB and then message echo string, not string, say S and then self dot echo S and then message move, say point or something, say point, no point, and self dot move position the point P here. Awesome. So now let's see if this works. I don't know. Not found in the scope. Oh, point. Okay. I should have said point over here. Point. Okay. Let's run the whole thing. Should be able to see something. Well, the interesting part here is change color is a tuple thing. Like the type is like this is the enum variant. This is also enum variant. This takes a string. This takes a tuple. It's the data type over here. So this is like a function call or something like instantiating a thing of this type, and this is the type. So this is this tuple. So this one takes string data. This one takes point. This one takes a tuple, and the same tuple is basically used here. And you get a tuple here. So yep, interesting. Awesome, everything works. So you can keep working on this exercise. Cool. So you see here, when they say move, they mean like absolute move. I think it's not just adding and stuff. So it's just like move to this. That's all. And the echo is not even tested, I think. So that's just hello world. So it should have printed here, I think. No, it hasn't printed. Anyways, I guess that's all was there as part of this exercise. I'll see you in the next one. Bye bye.